Okay, I have two problems here that I would like for you to try. They are both solution stoichiometry problems. That is to say, we are running chemical reactions, and we're going to be using a dimensional analysis setup to solve the problem. Sample problem B is a fairly straightforward example of what we just did. We're looking for milliliters of that solution, and we're going to start out with milliliters of that solution. And I've given you a bonus problem here, and this bonus problem is also a solution stoichiometry, but notice what is happening here. I'm asking how many grams of a product would be generated by the reaction of two reagents, and I'm giving you, look at that, different amounts of my two reagents. So what is this? This looks like a limiting reactant problem. So this is a more challenging example. As a limiting reactant problem, what are you going to have to do here? You're going to have to run two stoichiometry setups, each of which is trying to solve for grams of silver chloride. Limiting reactant calculation 1 will be starting with the 120 mils of that silver nitrate solution. And limiting reactant calculation number 2 will be starting with 85 milliliters of potassium chloride solution. And then you would take the smaller amount of the two answers, and that would be your answer for how many grams of product could be generated. Recall that since these are stoichiometries, for both of them, you're going to need a completed and balanced chemical reaction for each before you do any of the other math. So a lot of things are coming together here. You're going to have to read the problem, write the equation, complete the equation, balance the equation, and then do the stoichiometry. Here you're going to have to write the equation, complete it, balance it, and then run the two stoichiometries and take the smaller of the two to be your theoretical yield, okay, because it's a limiting reactant problem. So if you would, give it a shot. Go ahead and pause the video and work through both of those. See if you can work through both of them. And when you're done, we can come back and I'll work through these problems. Okay, coming back from pausing the video, we're going to start on this first problem, and we first need a balanced chemical reaction. And you may recognize this reaction. It's one that we've used before. It's our lead 2 nitrate and potassium iodide. We use this as an example in our net ionic equations. The lead is it's a double replacement reaction. The lead 2 ion is going to pair up with iodides, lead 2, and therefore I need 2 iodides. And by the way, that is a solid, although its state is not critical for this problem. And then potassium pairs up with nitrate. Potassium is a +1, nitrate is a -1, so I only need one of each, so I do not have parentheses or more than one nitrate there. And by the way, that is aqueous. Balancing the equation, 1 lead, 2 nitrates, 1 nitrate, so I need 2 nitrates. 1 lead, 2 nitrates, 2 nitrates. 1 potassium, 2 potassiums. So I have 2 potassiums now. 1 lead, 2 nitrates, 2 nitrates, 2 potassiums, 2 potassiums, 2 iodides, 2 iodides, and it's balanced. So now it says how many milliliters of this solution are needed to react with that many milliliters of that solution. So this is the quantity, the amount that I'm given. That's where I'm going to start with. 55 milliliters of the lead 2 nitrate. And I'm looking for milliliters of the potassium iodide, so I'll put that way over here. Give myself plenty of space to work on this problem because we know I'm going to have to go through several conversions. So milliliters to liters, liters to moles, moles to moles, moles to liters, moles to milliliters, right? So that's what we're going to do. Milliliters to liters of this lead-2 nitrate. Then liters of the lead-2 nitrate to the moles of the lead-2 nitrate. Now I've got moles of this. I'm going to convert to moles of the other substance through my mole to mole ratio. So I've got moles of lead-2 nitrate to moles of the Ki. Now I've got moles of Ki, and I'm going to convert from moles of Ki to liters of Ki using my molarity. And then now from liters of Ki to milliliters of Ki. And there we go. And plug in numbers. 1,000 milliliters to 1 liter. 1,000 milliliters to 1 liter. Molarity conversions are always per 1 liter, right? The same way that molar mass conversions are always per 1 mole, molarity conversions are always per 1 liter. How many moles per liter of the lead-containing solution? It's 0.25. How many moles of the potassium iodide per liter? It's 1.5 moles per liter. And what is my mole to mole ratio here? For the potassium iodide, it's 2. For the lead-2 nitrate, it's 1. And I do this math. And my answer is 18.33, which rounds to 2 significant figures. And it just so happens to be coincidentally 18 milliliters. That happened to be the same answer as my previous problem, but that was just a coincidence. And there we go. We've solved the problem. Now, if we move on to the bonus sample problem, now if you'd like to, having gone through this problem up here, maybe you want to take a moment to pause the video and see if you can rework what you've done down here. So I'll let you take a moment to do that. Go ahead and pause the video if you'd like. All right, coming back from that, or moving on, if you chose to move on, we're going to solve this problem down here. We need a balanced chemical reaction first, so that's what I'm going to do. How many grams of silver chloride would be generated by the reaction of silver nitrate? So I've got silver nitrate and potassium chloride. So this is a double replacement reaction. The silver is going to go with the chloride. Plus 1 silver, minus 1 chloride, I only need 1 of each. The potassium is going to go with the nitrate. Plus 1 potassium, minus 1 nitrate, I only need 1 of each. Again, the states are not really critical in this because I'm not trying to figure out whether one of them is going to be precipitated or not, but it just so happens that that is a solid and that is aqueous. These are also aqueous. The state indicators are not critical to being able to solve this problem. Is it balanced? 1 silver, 1 silver, 1 nitrate, 1 nitrate, 1 potassium, 1 potassium, 1 chlorine, 1 chlorine. It is balanced. So now this is a limiting reagent problem. How do I know? Because I'm asked for how many grams of a product are generated, and I'm given different amounts for the 2 reagents. So I've got to figure out which of these reagents generates the smaller amount of product, and that's going to give me my theoretical yield. So I'm going to set up my limiting reactant calculation number 1 and a limiting reactant calculation number 2. And here we go. I'm going to start the first one from the 120 milliliters of the silver nitrate solution. And way over here, I'm going to answer with how many grams of silver chloride. And similarly, for my second limiting reactant calculation, I'm going to start with the quantity of potassium chloride I'm given, which is 85 milliliters. And way over here, I have to come to the same destination, right? Grams silver chloride. And when I get these two answers, I'm going to circle the smaller of the two. That's going to be my theoretical answer, my theoretical yield. So we know how to set these up now, right? And so my answer then becomes 4.0. And which of these two is the correct answer? It is the smaller of the two, and so the correct answer is going to be right there. And so the silver nitrate is my limiting reagent. Even though I had more volume of it, it ended up being my limiting reagent at the end because it gave me the smaller amount. So of course I need to circle my answer because that is the correct answer. And this shows that you can do solution stoichiometry even with limiting reagent problems.